uh, like weird taste in the mouth and a lot of pain in the neck. Um, but I don't know, it wasn't that bad, and I'm still a bit uh, like I have to go to bed after this, like just to
Mm,
save energy.
still
Yeah,
recovering.
yeah,
How long have you had it for?
yeah. 6 days approximately,
Mm.
1 week. Yeah, this is just the two of us today. It seems.
Probably we'll get a few more, but I do want to start early because it's very ambitious. I don't really know what I'm doing, but I think we can make some progress. I have some ideas.
Do
So,
you
hmm?
do you know about Alpha Zero? Alpha Zero,
A what?
like, like the computer that beat the best computer that plays
Oh, Alpha
chess
Zero.
now.
Yeah, Alpha Zero. Yeah, yeah. Deep Mind.
Yeah. What are we going to do similar to that?
Exactly. We're gonna do even better.
Really?
Well, possibly.
Okay. If you do
Hey,
better,
what's up, guys?
Hey, Jake. Welcome.
Hey, man. Hey, when can we onboard you as a hatcher?
I guess after this lab.
Well, we have our steward planning call after that for 2 hours.
Okay. I'm usually free Friday afternoons, so this afternoon sometime.
Okay, how about five five my time is three. No, it's 3 your time.
Yep.
How about that? Is 3
Yep.
p.m. work for you?
Yep.
Love it. All right. Thank you so much, Sean.
You're welcome. Thanks, Jake.
Yeah. How you doing, Tonga?
I'm fine. I'm better, but not
Yeah,
completely. Yeah.
that's good. You were sick. You had COVID, you said.
Yeah. Fucking virus.
Well, I'm glad you're doing better.
Yeah. Thank you. How are you?
Yeah, absolutely. Hey, Sean, are you gonna do some more crazy like universal math stuff?
Uh, at some point. Oh, what, Matt? Oh, you mean the Gitcoin stuff?
Is that what
That's
you
not.
got, dude? I was so lost. All I
Yeah,
saw was mathematical equations, and then you guys were just going, and I was
Danilo's the
like,
master
whoa.
scientist. He is the most advanced like data scientist I've ever seen.
It was pretty hard to walk into. Yeah. Is any more of that going to be going down
Yeah,
though?
that's every Thursday. There's live hack sessions. Actually, next Thursday I'm doing a little bit of a session on AI. In that, so yeah, that's the most advanced class on Thursdays. But
God, if
I don't want to get too distracted here because we're gonna try to
oh
implement
yeah, I'm sorry, I'm bugging.
a
Okay.
whole chess
Yep, I'm out.
simulator.
Yep, love you.
Thanks, Jake. Hey Juan, nice to have you here. Sorry I missed the Graviton session yesterday. I had just too many things happening yesterday.
Don't worry. I'm happy to be here and thank you.
Oh, thank you. Okay, so I'm gonna make sure that we have this pinned in the new lab channel here. Oh, maybe I can't pin it. Um, okay, guys, so go ahead and open up the Notion workspace. And let's hit the attendance sheet. Okay. Insert. Sweet. Okay. Nice. So yeah, today is quite an ambitious feat. I was a little bit stressed last night worrying, but I think we'll just have some fun with it and see how far we can get. Lab 13. I must have missed an attendance day, but that's okay. ChessCAD. Okay, so I should have probably put some agenda notes in here beforehand, but that's okay. So first we're going to grab a template. Get a template for CAD. Then we're going to implement chess state variables. So how do we represent a game of chess? And so it's going to be the board and which player's turn it is. That's essentially most of what we have to do. We're going to have to implement the moves, which will be the difficult part. And then we're going to have to implement the player logic so that a player can understand what moves they have available and then choose a move. And essentially that, and then we run the simulation.
Is any part, like in the programs of chess that I know, there is like an evaluation, the position, like which one has the edge at which point. So yeah.
Yeah, that's a good question. So I think part of this implementing the state, so maintaining the state, we can keep track of captured pieces, and so we can sum up their points. So we could have a score. Now it would be
Yeah.
hard to have. That's a kind of a naive, I think. Well, yeah, that's like a base, so we can do that. I was thinking of that as well.
Yeah, that's like basic. It's good to start. It's not all, obviously, but
Yeah.
yeah.
Okay. So I'm just in the labs directory here, and I'm gonna grab. Okay, maybe I need to remember where it is. So in the research group with Gitcoin, I gave a presentation on reinforcement learning in the simulations, and I made a really simple example. So I'm going to see if I can jump to Gitcoin research, and I should have a notebook here that is called, yep, it's this toy reinforcement learning. Okay, so I'm just going to copy that here. So copy home / workspace TEC Gitcoin, and then it's called toy.rl and /. Okay. So we have this Jupyter notebook that has a nice template CAD in it, and then I'm just going to activate my virtual environment and open that up. Okay, so this is pre-baked for us. So we have our CAD imports. Let's see if we have everything installed. Yep. Okay, so here is our system parameters. So I don't think we'll have to worry about this too much. I'm going to rename this to be ChessCAD. So I'm not sure if we need really any system parameters, but we might. We can come back to this. I'll just leave this in here as an example.
Yeah, I was gonna say colluders on the chessboard. What is going on?
Yeah. Initial state. So this is really it. This is where most of the setup is going to happen. So we're going to think about how do we encode a chess game. So first we're going to have to make a board. Well, we're going to have to represent the pieces to start. So everything you're going to see here, it just came to me in a dream. I've just been dreaming about this stuff this week. So, and I also did a similar assignment once in my undergrad, so I kind of have some faint recollection of that. So we're going to have to represent our pieces. So imagine in your head now, sort of visualize the chessboard, right? And so this is why I'm glad Tonga's here. Tonga has a background in professional chess playing, so he's going to be able to catch some of the subtleties. So we have the pieces on the board. Starting at the corner, we have a knight, right? So I'm going to represent that with KN. And
The border,
oh wait,
the rook.
no, the rook. Okay, good that Tonga's here. Okay, so the rook and then the knight.
Yeah. Yeah, when you write in chess, you use the N only for the knight, I think.
Wait, what is it?
Because when you write the king, you use the K. So when you write the knight, only the N.
Oh, okay. B for bishop.
Yeah.
Okay,
Uh,
so let's visualize the chessboard. Let's say, okay, so the chessboard's in front of us. Let's say we're the white players. Okay, so let's actually start at the top, at the back of the board. So, you know, if from our perspective, we have the white pieces, um, and let's imagine that what we're defining here is the very back of the board. So it'd be the black pieces. Um, so do you know if it's going to be the queen or the king?
from left to right, the queen.
Queen.
Yeah.
And then the king
Then
is K. Oh, and do we need to
bishop.
Okay, I don't think we need to differentiate these different pieces. And then
The bishops might be useful to differentiate, but I don't know. Just one's on one color, one's on another. But
yeah,
it'll probably work out.
let's keep it simple for now. I think it'll work out. So let's say black pieces. And then I'm just gonna do this. I'm gonna go white pieces equals the p for piece dot. Since this is a string, we get this function called lower for p in black pieces. And then what that looks like is this. So this is going to make our algorithm super simple because we can always, when we need to know what moves black has available, we're going to check for uppercase pieces. So now we have black pieces, white pieces. We also need pawns. Okay, let's say black pawns equals, and just, is it P for pawn?
Yeah. Oh no. Usually you don't write anything. Just the square where you're moving to.
Okay, so I'll just put this so that we can keep track of it. So we need 3, 4. I think that's right. And then similar, let's do this. So white pawns equals p dot lower for p in black pawns. Okay, white pieces, white pawns. Okay, so now I think we'll just use an X for an empty space. So we're gonna have to compose the whole board. So the board is going to be a list of lists. So it's got this two-dimensional functionality. So we can set it up as it's like black pieces, which is already a list. So it's just black pieces, black pawns, and then we have, I'll make this like empty row. Empty row equals, just use x's, or maybe this number. We can change this later. Okay. So how many? 1, 2.
8 should be.
Okay. And how many empty rows are we going to have?
4.
4.
4.
Okay. Empty row, empty row, empty row, empty row. And then we have white pawns, and then we have white pieces. Okay, so let's take a look at our board, see what this looks like. Cool. Does this look right, Tonga?
Yeah, perfect.
I was not expecting that to work out so nicely. Okay, so that's our initial state. So this is what's going to change. The initial state is what changes over time in the simulation. The system parameters don't change over time. So I can't think of any system parameters that we need, but maybe maybe the players, maybe the type of players that we want to punch in later.
Yeah, one turn at a time. I don't know.
Yeah, like we could augment the game through these things. We could make different rules, for example, rule sets and stuff like that.
This is amazing. I can't believe you can just write in black pieces like that and it just works.
I know, Python is too powerful. Okay, so turn is gonna be starts with white, and I'm gonna make one. Oh, I wrote a bunch of notes in my notebook the other day. Let me flip to that page to see if there's anything I'm missing. Yeah, so we can have finished, false. We could have winner, none. We could have move number, 1. And then we could have captured. So captured, I think I'll make this a tuple, so it's like a pair of sets. So it starts off as a pair of empty sets. And we'll just say, basically this is player 1 and this is player 2, so we can say the white pieces are player 1 and the black pieces are player 2. So this is pretty good. We'll start with this. I think we might come back to this and add a couple things, but this is our initial state. Oop. Move number. Oh, here we missed a comma. Okay, so now it gets interesting. So we've defined the game, what the state of the game looks like. Now we kind of have to, let's jump back. So get a template, implement the state variables, implement the moves. So basically for each type of piece, we have to implement a move. Okay, so I don't know how long this is going to take. Hopefully we can do this in like 10 or 15 minutes. But so I'll just make M. I'll start all these with M for move, and then I'll just say R, or I'll just say rook. Okay, so, and I think what we're gonna have to do is we're gonna have to understand like indices of the board. So let's take the board and say it's a list, so we can say the first row and the first column is an R. Okay. So I think we're gonna call this is kind of a math thing. We're gonna call this I and call this J. So we're gonna get the position of the rook at I and J. And also we have 8 by 8, right? So let's just work with an example. So let's say I equals 2 and j equals 5. Then we can see where that is on the board. So board of I, j is a 0. It's too bad we can't like visualize this on the board. We probably could if we put some thought into it, but let's think. This is the second row and the fifth. Oh, so it's 0 index. So we have 0, 1, 2, 0, 1, 2, 3, 4, 5. Okay, so this is what I and j is in our example. So let's imagine that a rook was there. Then we're basically going to be able to go left, down, right, and up. So let's just try that. So it's going to be like, say, up, right, down, and left. Okay, so up means we're going to go 4. So we have I is our row. So we're going to be changing our I indice. So let's use a new indice called k, for which is it's where we're moving to. For k in range, and we're moving up, which means our row is going to be decreasing because row 0 is at the top. So we're currently at I. So we're going to go from I to 0. And I think we're going backwards, so we say -1. Let me just test that out. So for k in range, let's say 7 to 0, -1. That's our step. Print k. Yeah, so we go backwards to 1, but we actually want to go to 0. So I think this should be -1, because we can actually go to row 0. Okay. So for each of these that we can move to, we're going to check what occupies that space. So piece that occupies that space that we're considering moving to equals the board at kj. Okay. Now we can check if that piece is ours or our enemy's. So, okay, we need to know what player we are. So let's say player equals white. Then if player equals white, then if the piece is lowercase, then it's ours. If it's uppercase, it's the enemy's. So if we can do it like this, piece. So this piece here, this variable is going to be a string. It's going to be like uppercase P or something like that. Or yeah, it won't be a. Okay, the first case is that the piece, if piece equals 0, then it's empty. So we can move there, and we can also continue. So we're going to continue. And what this keyword does, it means it means just go to the next step in the loop. Don't even evaluate all the logic that comes next. Just keep looping. And that's what we want here, because if it's a 0, we can just keep going. And if it's not, then we're going to check if the piece, and we can say dot lower equals the piece. That means the piece is lowercase. So if we're a white player white pieces, then this means it's our piece. This is our piece. This is our piece, and we cannot move here. So that means we can move from indice I to indice k minus 1 going up. See, this is getting quite complicated fast. I was worried about this. How much time? Maybe I should have pre-populated these beforehand. And this is only the rook, and this is only moving upwards. So, dang. Okay, let's just keep going, I guess.
Yeah, I was really surprised that you were going to in 1 hour. It's like people have been solving this for years, trying. So
Yeah, well, this is the cool part. It's like if we get all the logic wired, then we can just throw it at ChessCAD, and ChessCAD will simulate. I mean, there's two pieces. So actually, also in this template, so we have all the ChessCAD here. Then I have some reinforcement learning agents. So if we could just throw them in the simulator and have them run forever, then theoretically we could just make some really, really powerful chess AI bots.
I mean, the queen is just the bishop and the rook.
Oh, good point.
The knight has a pattern. So you need to do rook, knight, bishop, and king and pawn. And then everything should be done.
let's see how it goes.
Okay, so in this case, we've found our own piece. So that's as far as we can go. So this is going up. So max up equals should be k. I think it's going to be +1 because we're going up, which means actually we're decreasing our indice. So, and then we're going to break this loop. So if we go break, then we should quit out of this for loop. Now there's the final case here. Else if piece dot upper. Well, it should just be else. There shouldn't be any other cases but let's check it like this. So this is our opponent's piece. So actually, we're not going to do any crazy logic. We're just going to say that this is as far as we can go. So our maximum up is k. And we'll break out of the loop. And I'm just going to put a final else statement here that says raise. This is going to raise an error, and it's going to say print. We shouldn't end up here. We shouldn't end up here. And just so if we end up here, then we know there's our logic isn't quite right. Okay. So then let's just do the same. If player equals black, then we should be able to copy and paste this. And Griff is right. It's going to be about reusing functionality. If we can reuse logic, like if we can make some functions out of this, and then we reuse the rook functionality for the queen, that's how we're going to get out of this complexity. So now it's just the opposite. So these cases are going to switch. So if it's a lowercase piece, then it's our enemy. This is our enemy. And we can attack it. And in the other case, this is our piece. So we can not move to it. Okay, so this is moving up. Now we have to do this, I think, for all the directions, although it's the same logic. Let's see if we can reuse this. So, yeah. Yeah, it's just the for loop that's going to change. So let's make a function def check check line or check. It's just a single point actually. Check point compatible. I don't know. Checkpoint for move. So let's take all of this logic, put it in here, and this is, we need K, J, and player. Okay. Yep. Cool. Continue.
Let me just say, this is already the best lab that I've ever done. So this is amazing.
I've
I'm really enjoying.
been really excited for this. It literally came to me in a dream, and I couldn't stop thinking about it. Not sure what this. Oh, is it just indented too much? Maybe. No. Continue not properly in loop. Oh, we're not in. Okay, so let's just try like return. No. Oh yeah, return 1. So like if it's 1, we keep going. If it's 0, we're gonna break. Return 0. Let's try this. Okay, so now we go whether or not we continue, or let's just say, yeah, keep moving equals checkpoint for move, and we have K and J and player. Okay, and then oh, we should actually return the K. So in this case, let's return -1, because we should never, K should never be -1, because that would be off our board. So if it's -1, it means we just keep moving. Otherwise, we're going to return K plus 1. Let's return K. And here, let's return K. And here, we'll return K plus 1. Okay. So if now, if keep moving equals -1, then we continue in our loop. Else max up equals keep moving. Now that the naming there is maybe a little bit, let's just call this check. Okay. So that's for going upwards. So it's just how our loop changes. So now we should be able to just repeat this.
Check might be confusing for when you actually check the king.
What's that, Tonga? Did you say you're confused on the check part?
Check and checkmate, you know? It's just not necessarily avoid the word check.
Yeah. Good point. Yep. I'll call it evaluate. Or what do you guys think, Tonga? Maybe you have an idea. What should this function be called?
I think as it was before, it was okay.
What was it?
I don't remember.
I'm just gonna call it evaluate. Sure. Evaluate move. No, because that's like, what's the performance of the move? Movable is can
Move, move step, or is I mean, what does it do?
it's checking it's checking how far we can move. It's checking if it's checking if a certain point on the board we're allowed to move to.
Move allowed.
Yeah, yeah, that's it. Allowed. And this is still a little confusing because -1 means we can keep moving. But that's okay. Whew. Okay, so we got 3 of these. We need 1 more. Okay, so now we just need to change these loops. So here we're going upwards, and that's why it's max up. Okay, this should be, we'll call this max left, and max right, and max down. So let's put some space in here so we can see up. Okay, this is left. Oops. Right and down. Okay, so when we're going left, we actually want to, so we're considering our column now. So that's actually J. J is our column. So we start at J, and we're going to the same thing. We're going to decrease because 0 is on the left. So this is actually right. Now if we're going right, we're going to 8, and we're going by +1. And same here for down. This should be 8, and this should be +1. Okay. So now I think this in theory should work, and let's see if we can think about how to test it. So we have these 2 functions. So let's go. It needs the board as well, doesn't it? What do we have here? Oh yeah, see, this needs the board. So let's pass the board in here. Maybe I'll pass it first. And we have to pass it to all of these. So now we should be able to say move the rook for, move the rook that is at, we have a rook here at 0, 0, right? So if we say board, board 0, 0, so board is the board, and 0, 0, and the player, let's say that player is black. Black. Didn't return anything. So let's return return max up, max left, max right, and max down. So it says we can go up and left. What do these really mean? 1 and 7. Let's take a look at our board again. So we're talking about this rook here. And one, I think it's, so is something not quite right?
I mean, he shouldn't be able to move at all, for sure.
Yeah, so what are these really? We're checking the range and we're checking the allowed move. So let's just think about how much we can move up. So let's print kj and let's print allowed. So it's saying at 0, 0, so that's good. It's checking our current position. And it's saying max up is 1, so I don't think that's correct. So let's check that. Allowed equals move allowed. Okay, so it's returning 1, 1. It's returning 1. And it's checking how far up we can move. So it's getting the piece. It's checking 0, 0. So it's getting the piece on the board, which is going to be a capital R. Piece will be a capital R. And the player is black. And yep, this is right. So it's going to say, it's checking 0, 0. So it's going to get piece dot upper should equal the piece. So capital R equals capital R. That's what this is saying.
K plus 1.
Yeah. Okay, maybe this should be K and the other one should be K minus 1. This is typical computer science. Everything's always off by 1.
Would it be K minus 1 or would it be K plus 1? I think it would be K plus 1 for if it's the other piece, because you can go into that piece's spot, right?
Well, it depends if we're moving. Kind of depends if we're moving up or down.
Oh yeah, that's true.
We might have to catch for that.
So you're right, because, well, in this case, moving down is plus 1, and moving to the right is plus 1.
Yep.
Correct?
Yep. So this is just off. This is like inverted. This should actually be 0 instead of 8. So that's when we're checking for right and down. So right, we're going from 0 to 8, and we're checking each allowed move. And if allowed is -1, so let's check max right. So again, same thing. We're going from k equals 0. So this is going to be 0, 0. And it should return, it should trigger on the first iteration, but it's not. It's going all the way to the end. Okay, this one seems to work for now. Let's take out these print statements and let's just put them here. And print allowed. Yep, so it's going all the way. So it's seeing zeros. Wait a minute. This should be the return. That first one. We need to get out of this loop. So there should be like a break. I think we should put break. Yep. Okay, so now it's saying we can't move at all. So let's try a random one. Let's put a random R in here. So let's recreate our board. And let's create like a special test row equals all of these. But let's put a random black rook. And we'll just put that in here. Test row. So now we have this rook here at 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. It should be at 4, 4, so let's check our board. Board 4, 4. Yep. Okay. So now let's test our function. 4, 4. Okay, so it's telling us that we can move in all directions 4. But that doesn't quite seem right either. We should be able to move left 1, 2, 3, 4, and right 1, 2, 3, and down. We should be able to take out this pawn and only move up 2. So we should be able to move down 2 and up 2. So it's buggy. It might.
Yeah, one of them right. One of them's right.
One of them's right. This is a good point. Good observation. Yes, Griff is so sharp. Okay, so moving left is correct, it seems. Which is this second one. That that might be useful information. But
Hey, why did you? I didn't want to complicate it much for you because it was already complicated. But in the boards, usually we see stuff like we make the board 8 by 8, and then we call the first line A, the second line B, the third line C, and from the bottom to the top, 1, 2, 3, 4, 5 until 8, and from left to right, A to H. That's how the moves are called. I don't know if that's helpful for
yeah,
left to right.
yeah, Tonga, I was actually thinking about this. So from bottom to top,
1 to 8,
1
yes.
to 8. Yep. So this is cool to know. So we can put this in there. It'll make it more realistic. And it could possibly simplify things, because then we'll be able to visualize easier which step we're on. So I think after the hour's up, I think I'll refactor this a bit, but hopefully, let's see if we can get this rook move working.
And left to right, the letters are lowercase, right, Tonga?
Yeah.
Cool. Okay, so let's just think about moving up. Yeah, let's think about moving up. So it should have 2, should be able to move 2. This should be 2. So let's take these out. Um, 4. It immediately returns 4. Allowed -1. So it should actually allowed should be -1 on the first. Oh. Oh, it's checking the value that it's on. It's checking 4, 4.
It's really saying it can't move. right?
Yeah. It's saying, "Hey, this is my own piece. I can't attack it, so I can't go anywhere." So we need to skip the tile that we're already on. So it's just this loop. So
So it should start with +1, yeah.
or -1
Or
in this
-1.
case. Hmm.
What is interesting for me is that you are making, like, in this array, it's like you're making, this is either a piece or a square. Or like in chess, we think a piece is in a square, but here it's like if it's an empty square, or a piece, you know.
Yeah, good point. We're not really modeling the squares, and I thought about that too. And Griff mentioned something like the black and whiteness is somewhat important, right? But I was thinking, can we get a full simulation by going around that with just modeling the pieces instead of the squares?
I think you can.
Yeah.
It's just interesting to point out too, for sure.
Yeah. So this is still so it's saying up we can go 1, but I think it should be 2. 1, 2. Okay, so unless it's like 0 indexed, but anyways, these are definitely incorrect yet. So let's keep thinking. So we're going up. So it checks this.
This was so good. I'm sorry I have to leave right now, but this was so good, YGG. I'm definitely gonna send this video. This was really interesting. Thank you so much for this.
Thanks, Griff. I think it'll be awesome when we actually get this thing running and can have this chess simulator. I think this will be a good academic resource, educational resource for people to tinker around with. Yeah.
Absolutely. Thanks, man.
Yep. Thanks,
Thank
Griff.
you. Welcome.
Okay, so 3, 4, 2, 4, 1, 4. Oh yeah. Actually, this is correct. Wait, no. No, it's not quite correct. So it's 3, 4, 2, 4, 1, 4, and it should return. So it realizes that it can't go there. So it's checking 1, 4, which is here, and it returns a 1. Oh, so when it returns, so it sees that it's our own piece, and it returns k plus 1. Oh no, it sees that it's our own piece. Okay, so this depends which way we're going. So there's a bug in this. Because it depends if we're ascending or descending. Um, hmm. It's going to be these +1s, or so this +1 and this, it depends on whether or not we're ascending or descending. So it differentiates, like, so basically up and left are going to be different from right and down. I wonder if using this kind of notation would actually help us out of this.
Yeah, I was wondering, like, for example, for the rook, when we teach chess, we teach people, yeah, the rook goes straight up or straight left or straight right or straight down, and then you tell, okay, it can't capture your own pieces, but it can capture the enemy's pieces. It's like in a more human language, but I'm having trouble understanding a bit what you're doing.
Yeah, there could be a completely different way of computing this than this approach. Um, we might be able to simplify all of this into a single case that's just like move forward. And so it doesn't need to know which direction it's moving. It just knows that it can move forward. I guess that's what this is. But I think I'm going to have to refactor this code. This was a single approach. So we're definitely going to have to do a follow-up lab. We're going to get this working, Tonga. And maybe,
Yeah.
Tonga, we can do a session outside of the lab.
Yeah, let me know. I'm in for it.
Yeah. I think I'm going to play around with this a little bit offline and come back. I'll get a bit more prepared.
I have another idea because after chess I played poker for many years, and there is a lot of poker simulators.
Okay, excellent.
Yeah, I like those simulators. They are not open source. They are closed source, and like they are sold very expensive. So yeah, that's another idea for another time
Yep. First chess, then poker.
if you want, obviously.
I would love to do that. That's so cool.
Okay.
Okay, so unfortunately we weren't able to. I was a bit overambitious thinking we could make the whole chess game, but we're definitely gonna get it.
Yeah.
Yeah.
Let's do it.
Yeah. Yeah, this is too complicated, I think. I gotta simplify this.
Maybe if I was trying to do this, I would, I would look for other solutions.
Yeah, there's probably some, let's see, Python implementation of chess. Here's GitHub. Ooh, look at
maybe
this.
get some ideas. Yeah.
So it's very similar. Init player turn equals black. Interesting. They start on the black player's turn. Oh, probably because it switches turn at the beginning. So, no, that'd be interesting. Yeah. Oh yeah. So place piece. Oh, look at this. For iron range 08. So it makes the game board very similar to what we made. Oh, they make classes. So they have like a pawn class. And they give it a color. And they use a dictionary. And interesting. So where are their pieces defined? Here's a piece. Look at this. Class piece. So it has a color. It has a position. Oh yeah, this is so good.
Then maybe there is a way to mix this with CAD.
Yep.
But making the whole game seems like.
Well, this is only, look, this is only 240 lines.
Yeah, it's not that much.
Oh, and they use, this is what my roommate was just saying. He said check for Unicode. That's exactly what they're doing here. They use these Unicode text characters to actually, because these are, the chess is actually built into text encoding.
Okay.
Oh, see, okay, so here's the available moves function. So it's given the game board. See, this is very similar to what we were making. This is just a bit more elegant. So it returns XXYY for XXYY in king list. Okay, so they have this king list XY. Oh yeah, and then they have a function no conflict. Interesting. So where's this king list? Knight, Knight list. Okay. And
Also,
mhm.
before we finish, um, like in the reasoning, you were only going to add capture pieces, but there is a lot more. Uh,
How
in
is
the
it computed? Like the score?
Yeah, that's what I've wondered many years. But there is like a lot of different computers, and they assess differently than positions. So it's not something that is like unique. And there is better computer than others. So
Okay. So that's a whole like design process in itself, being able to compute the value of different moves.
yeah, and also sometimes you make sacrifices. So you are down in pieces, but your position is so good, so coordinated that still you have the edge. So it's a mix of.
Very interesting. It'll be really fun to when we apply AI into this. I have some AI systems in this very same notebook. Um, these stable baseline agents that use reinforcement learning. So basically, they're just going to observe the board, and then they'll get back a set of legal actions that they can take, and they're going to take an action. And these algorithms have like this deep learning policies built in, so that they start to learn how to map better and better actions based on the reward. So the reward will be essentially if they win the game or not. Or we could, if we had this system of evaluating the board
Yeah,
state, then the reward could be getting a better board state. But like you said, they might need to make sacrifices sometimes. So
you if you have like 3 minutes, you can go to lichess.org, and they have an access module for free. Lichess. It's Li chess, and that's even open source. Then you can go to tools, analysis for, and then you see stockfish at the top right, and there is the plus 0.3. That's the evaluation of the position.
cool.
So whenever it's going to choose a move, it's going to choose the move that has the better evaluation after.
So is it choosing the optimal move for each piece, for each turn?
Well, the optimal for the time you are letting it think. Like maybe if you leave it like
Oh,
more time, it changes. Yeah,
huh.
sometimes. You can add more variants. It can tell you the best, the second best. They're at the top, I think, in the settings somewhere. Uh, yeah, I don't see it. You see there at the top right, it tells you a whole variant.
This
Like
is
it says,
it's almost symmetric. This game is almost symmetric.
not really. It's not really. You can see, for example, the pawn on d6. You see d6? Can you?
6. So, oh, D6, this one?
Yeah. So white don't have a pawn on the d file. So that pawn is like a weakness because it cannot be defended by other pawns. And there is so much. It's not symmetric at all. There is other positions that are symmetric. Like this one. This is like the opposite. This is like game and counterplay. one player plays on one side, the other.
Huh. Oh yeah, there it changed.
And AlphaZero made so much progress for chess. Like
Oh.
the top players started copying AlphaZero
Wow.
so much. Yeah, it changed the game
Wow.
forever. Yeah. For example, AlphaZero loves to move the pawns from the A and the H file. Move a lot those pawns
Oh, okay.
from the borders. Yeah, yeah, it's really complex. And this whole site, leeches.org, I think it's all open source.
Cool.
The, the whole site. Uh,
Yeah, this looks
yeah,
awesome. I met a friend, I made a new friend recently, and he got me on, I think it's just chess.com or something. Is that right?
yeah, there is chess.com and chess24.com, but those are a bit more private, and the open source site crashes it. Everyone loves it.
Cool. Okay, well, I think I'm gonna sign off, Tonga, but thanks for all the advice. I think we should probably just grab this next time and put it into CAD.
Yeah, let's see how to do that.
Yep. Yeah, we can have
Thank
some
you.
fun with this. Yep.
Thank you, White. Thanks a
Thank
lot.
you. Yep. Thanks for
Thank you, Juan, for coming.
Thanks, Wonka. Okay, I'll see y'all later.
See ya. Bye.
Bye bye.